Welcome to the third module. So, let us again as usual begin with the quick recap of what we had done in the last two modules. So, we started with our basic ansatz for an oscillating system. The oscillating system could be anything, but nevertheless the basic physics is that the restoring force is proportional to displacement with a negative sign, and this is true in the limit of smaller displacements. Now, if you follow this thread of logic, finally you end up with an equation of motion which is given here right in front of you, and omega here is the angular frequency. So, in the last module we saw that given the displacement being a function of time, and we were able to obtain the functional form which satisfied this equation. So, for example, we could one possible solution that we wrote down was to say that displacement was some a sin omega t plus phi, where phi in general is some phase. And if I try to plot these sketch these functions, that is what I have here on the right hand side. So, displacement as a function of time is a sine curve, just as I have written it down here, and velocity is simply the first derivative of the displacement with respect to time, it is shown here, and acceleration is the second derivative of displacement with respect to time. So, all that is sketched here, and we also saw that we could calculate the total energy of an oscillating system. It is made up of kinetic energy and the potential energy. So, the total energy is sum of these two energies. So, individually when you calculate the kinetic and potential energies, each one of them, each of these components is a function of time. So, they vary with time, but quite miraculously they vary with time in such a way that the total energy is a constant. So, if I were to sketch the total energy as a function of time, this is what I will get. Basically, it is a constant flat line as a function of time. And again we rationalized it by saying that when we started writing down the equation of motion, we did not allow any avenue for the initial energy that is given to the system to be dissipated. So, when I start off an oscillation, say in a pendulum or in some other oscillating object, I give it some energy, and the energy does not really dissipate itself. Of course, in real life there would always be dissipation, and we will deal with dissipation in one of the future modules. Today we will look at how we can combine more than one oscillations in the same dimensions as well as in perpendicular dimensions. So, this will be the remit of this module and the next one. To be able to do that, we need to slightly liberate our ideas, in the sense that you can have any sort of an oscillating system. So, I have a pendulum here, I have a U tube with some liquid in it, and if I press the liquid in one of its arms, it is going to start oscillating up and down. So, that is an oscillatory system, and I also have a mass which is hanging from a rigid support through a spring. So, if I pull it down a little bit here, and I can make it oscillate up and down. So, that is an oscillatory system, and I have a two body problem here. Maybe you can think of it as a sun and a planet that is going around the sun, for instance. This can be thought of as an oscillating system. We will see how rotations can also be thought of as oscillations in one of the later modules. And I also have an LC circuit. So, you can actually construct a whole lot of different systems where you will see oscillating solutions, or oscillations do happen physically in such systems. Now, when you go to the limit of small oscillations in all these cases, finally you will end up with an equation of motion which looks exactly like this. So, in all these cases the governing equation of motion is simply a simple harmonic oscillator. And since we already know the equation of motion and we have already written the solution, which means that every time we come across a new oscillating system, we do not have to reinvent the wheel in some sense. So, we could basically straight away write down the solution, just like the way I have already written it down here. So, this simply says that it does not matter what the system is until the system actually shows oscillatory behavior, and in the limit of small oscillations I can always assume that the solution is of this form. So, now when I am going to combine oscillations, two oscillations in the same dimension and so on, I will not even specify a system. So, this implies that this could have come from any of these systems that I have here, a pendulum or a mass that is hanging from a spring and so on. It does not matter, all these details do not matter until it is an oscillating solution. So, all that would matter for us, at least for this module and the next one, is that we are dealing with an oscillator, which is described by an equation of motion that is shown here, and its physical origin is more or less immaterial for our purposes. So, with this background, now let us get to the next level of complexity. So, the idea here is to superpose two oscillators in one dimensions. Okay. So, it is like having two pendula in the same dimension, or maybe in some way two oscillating systems, but essentially both of them are oscillating in one dimension. And I would like to know what is the net oscillation if I combine two oscillations in the same dimension. And the restriction that I place is that I have two oscillators and they have same angular frequency. So, which means that I can start with the following ansatz. So, I have two oscillators, and without going through the grind that we went through in the first module and the second module, I will directly write down the solutions. So, that is there right in front of you. X1 represents the displacement of the first oscillator, and A1 is the amplitude of the first oscillator, and phi 1 is the phase of the first oscillator, and X2 is the displacement of the second oscillator, and A2 is the amplitude of the second oscillator, and phi 2 is the phase of the second oscillator. Now, I want to combine these two oscillations. So, which means that my combined solution x of t would simply be equal to x1 of t plus x2 of t. And this sort of writing down the solution as superposition of two solutions is possible simply because the equation of motion that we wrote down for the harmonic oscillations is what would be called a linear differential equation. So, in a sense, all we are doing is to implement a mathematical property of linear differential equations, that if I have two different oscillations and their solutions, a linear combination of those solutions would also be a solution. Okay. Now, let me complete this. So, x1 plus x2 would be a1 cos omega t plus phi 1 plus A 2 cos omega t plus phi 2. Now, all I need to do is to use the cos A plus B formula and write it differently. So, let me do that. A 1 cos omega t cos phi 1 So, I have essentially used the cos A plus B formula, expand this cos A plus B term here and write it in full. Now, what I will do is separate out cos omega t and sin omega t. So, let me first take cos omega t. So, if I take cos omega t out, I will have A 1 cos phi 1 plus A 2 cos phi 2. And now, I will take sin omega t out, in which case I will get A 1 sin phi 1 plus A 2 sin phi 2. So, I have done nothing more than rewriting the former expression in a slightly different way. Now, the next step is crucial, because even when I combine the two oscillations, what I get is another oscillation. So, somehow the final result that I get should represent an oscillatory solution, and that I can do by rewriting this quantity within the brackets as cos theta and this quantity here I will write it as sin theta. In this case, this is again another expression for cos A plus B. So, I could write it as cos omega t plus theta. So, I know that when I combine two oscillations, I need to get another oscillation. So, looking for such a solution, let me do the following. It is cos omega t here, but you will notice that the quantity within the bracket is entirely a constant. A 1 is amplitude, A 2 is amplitude, both are constants, phi 1 and phi 2 are two different phases, both are constants. So, the entire quantity within the bracket is a constant. So, I could write it as some other constant or cos theta minus again sin omega t. So, the quantity within the bracket here is also a constant. So, I will write it as or sin theta. Now, what I have is simply another cos A plus B formula. This can be written as r times cos omega t plus theta. So, now I have the following result. So, x 1 of t is a combination of two displacements of the two oscillators, and that is simply equal to r cos omega t plus theta. So, what we have obtained is what we were expecting to obtain, namely that when I combine two oscillations I will get another oscillation. So, the solution that I have got is indeed oscillatory, the phase here is theta and the amplitude here is r. So, clearly I have now got two different constants r and theta, which at this stage I do not know what they are. So, they need to be determined from the properties of the original oscillations. In other words, these two new numbers that I have introduced r and theta should somehow be related to A1 phi 1 and A2 phi 2. And it is not very difficult to obtain these relation if we simply write down what is r cos theta and r sin theta. So, let me first write it down for your benefit. So, I have r cos theta and r sin theta written in front of me, and now from here it is obvious what to do. So, if I want to find r, all I need to do is to square and add both these equations. If I do that, I am going to get the following result. If I square and add these two equations, I will get an expression for r square, which looks like this, and if I divide r sin theta by r cos theta, I will get an expression for tan theta, and from this expression I can write down an expression for theta as tan inverse of these constants that I have here. So, now I have determined both r, which is the new amplitude, and the new phase theta in terms of the original amplitudes and the phases. So, the original amplitudes and phases were A1 phi 1 and A2 phi 2, and the new amplitude r and the new amplitude phase is simply a function of A1 phi 1 and A2 phi 2. So, when I put together two oscillations in the same dimension, all I get is another oscillatory solution. The only difference is that the amplitude of the new oscillation and the phase of the new oscillation are dependent on the amplitudes and phases of the two sets of oscillations which were combined together. And if you notice in this expression for r square, you notice that there is a term phi 1 phi 2 minus phi 1, which is simply the phase difference between the two oscillators. So, the new amplitude r is going to depend on the phase difference between these two oscillators. Let us say that I choose phi 2 minus phi 1 such that the term cos phi 2 minus phi 1 is equal to 0, and this would happen if for instance phi 2 minus phi 1 is pi by 2, for example. That is one value of phase difference for which cos phi 2 minus phi 1 would be 0, in which case r square would simply be equal to A1 square plus A2 square. On the other hand, suppose let me consider another case for which cos phi 2 minus phi 1 is equal to 1. So, this for instance would happen if the phases were exactly the same. So, phi 2 minus phi 1 is equal to 0. In that case, cos phi 2 minus phi 1 is equal to 1, and then r square would simply be equal to A1 square plus A2 square plus 2 A1 A2, that would be equal to A1 plus A2 whole square. We can look at another limiting case, which is when cos phi 2 minus phi 1 is equal to minus 1, which could happen when phi 2 minus phi 1 is equal to, for instance, pi, and this would give me the following relation, that r square is equal to a 1 minus a 2 whole square. So, clearly the value of the resultant amplitude r depends on the phase difference, and in fact, if you are combining two oscillations in which a 1 and a 2 are equal, and there is a phase difference of pi between the two oscillating systems, the resulting oscillation would have an amplitude equal to 0. Okay. That is something spectacular. You have two individual oscillators, you combine them and they do have a phase difference of pi, in which case interestingly the resulting oscillation has an amplitude 0. So, now let us go to the next level of sort of complexity. So, earlier we combined two oscillations in one dimension which had same frequencies, but different phases. So, now let us do a problem where we have two oscillators, but they will have in general different frequencies. So, corresponding to this situation, I can write down the following solutions. X 1 is equal to so, I have directly written down the solution. So, you should immediately imagine that there are two oscillators for which the solutions have been written down. The first oscillator is oscillating with an angular frequency omega 1, and the second oscillator is oscillating with an angular frequency omega 2, and these two oscillators are oscillating in the same direction or in the same dimension, and they are being combined together. Now, what is it that we can expect from these two oscillations? The general principle is the same. If I combine two oscillating systems, I am going to get another oscillating system. So, in fact, it is not restricted to just two oscillating systems. This way I could add any number of oscillating systems, and the solution of the sum of all of them would also be an oscillating solution. So, as usual, I have written down x of t is sum of x 1 of t and x 2 of t, which in this case would be a sin omega 1 t plus a sin omega 2 t. And I will also, without loss of generality, assume that omega 2 is greater than omega 1. It does not matter, but it just makes life somewhat simpler for us. Now, we will use again another trigonometric identity. So, this time we will use sin A plus sin B formula to resolve this. So, if I do that, I could rewrite this expression here differently. So, all I have done is to simply use the sin A plus sin B formula. So, what you see is that I have again an oscillatory solution. If you like, you could think of the solution to be some sin omega t, where the amplitude itself is dependent on time. So, to do that, let me just rewrite it slightly differently. Now, when you look at it in this form, you could think of this as oscillation whose frequency would be given by this quantity omega 1 plus omega 2 by 2. That is the frequency being the average of the two frequencies, and this entire term could be thought of as the amplitude. And the amplitude now depends on time. To understand how this basically plays out, let us try and plot out each of these terms separately. So, we keep in mind that omega 2 is greater than omega 1. So, the quantity omega 1 plus omega 2 by 2 is fairly large. So, you might actually get something like this and so on. Now, let me sketch the cosine term. So, if you keep in mind that omega 2 is greater than omega 1, you would notice that this number omega 2 minus omega 1 is smaller than omega 1 plus omega 2. So, clearly this is going to have a much smaller frequency oscillations. In other words, as a frequency, omega 1 plus omega 2 is larger than omega 2 minus omega 1. So, what we are going to have is something that is going to have a smaller frequency like this. Now, our solution says that these two components needs to be multiplied, and if I do that and sketch it here, what I would effectively see is that the cosine function would decrease in amplitude and so on. So, and what you are left with is an envelope that goes like this. So, here I have plotted x of t as a function of. So, there is this envelope which comes from the cosine term whose frequency is omega 2 minus omega 1 by 2, and then there is the fast oscillation which comes from which happens with the frequency omega 1 plus omega 2 by 2. And when we look at both of them happening together, in the sense that what we are actually experiencing is product of these two terms, and you get this waxing and waning of oscillations periodically, and this happens with the frequency which is equal to omega 2 minus omega 1. In the limiting case, if I assume that omega 2 is approximately equal to omega 1, but not exactly equal, in which case omega 1 plus omega 2 is approximately equal to 2 times omega, simply because omega 2 is approximately equal to omega 1, which is approximately omega, and omega 2 minus omega 1 is approximately equal to 0. In such case, in such a situation, the product of our two terms basically tell us that the sine term, this is going to do a fast oscillation because omega 1 plus omega 2 is large, and the cosine term here is going to do a slow oscillation simply because omega 2 minus omega 1 is very close to 0, a very small number. In such a situation, you end up with a phenomenon of beats, and beats have a frequency which is equal to omega 2 minus omega 1. So, when you combine two oscillations which have different frequencies, In such a situation, and especially if you go to a limiting case where the two frequencies are very close together, in such a case you can experience the phenomena of beats. You will see that the displacement essentially increases, goes to 0 and sort of oscillates in this fashion that is shown here. And typically when you do this experiment with tuning forks, what you actually listen or what you hear is simply the intensity of sound, which are related to squares of these quantities, in which case the beats would have frequency equal to omega 2 minus omega 1. Again, to summarize this part of what we have been discussing, we looked at how to combine two oscillators in one dimension, and the two oscillators have different frequencies. And when you assume that let us say that there are no phase difference between these two oscillators, it is very easy to write down the combined solution. As usual, the principle is that the net displacement is sum of the two displacements, because they are in the same direction or in the same dimension. And when you simplify it, what you see is that the net displacement is a combination of two parts, one which is a fast oscillation and the other one which displays slow oscillations. And when you try to sketch it, you see that the fast oscillation is being modulated by the slow oscillation, which shows up as the profile in with the frequency omega 2 minus omega 1 by 2 here. And when you take this to the limiting case where omega 1 and omega 2, that is the two frequencies are nearly the same, but not quite exactly the same, in that case you get what are called beats. There is strong waxing and waning of oscillations, and when you listen to two tuning forks which are held close together and let to oscillate, you do get very strong sound intensity that is increasing, decreasing and so on. So, that is the phenomena of beats. To summarize what we have been saying, we started by saying that you could be dealing with any kind of oscillator in the limit of small displacement. In all such cases, the governing equation of motion is the same, and the governing solution is in general can be written as a combination of sine and cosine with some phase to it. Then we dealt with the problem of how to combine two oscillators in one dimension, and here the restriction was that the two oscillators have the same frequency. And the main lesson here is that whenever you combine two oscillators, not just two oscillators, any number of oscillators, the net result is that the net displacement would also be another oscillator as shown here. And all you need to do is to work out the relation between the parameters of the original problem and the parameters of the combined solution, which is what we did here. The combined solution has an amplitude and phase, which is related to the amplitude and phases that were originally specified for the individual oscillators here. And then we looked at the problem of two oscillators again in one dimension, but with different frequencies. And here in this case, then we looked at the problem of again two oscillators, but with different frequencies in one dimension. So, in this case we showed that there would be strong waxing and waning of the displacement curve, and in the limit when the two frequencies are nearly the same, it gives rise to the phenomena of beats. Let us see how beats can be demonstrated with a simple cell phone that both of us have here. So, we are using an Android app which will generate for us pretty much frequencies in a wide range, and he has set his app to 434 hertz, and as you see I have set it to 435 hertz. So, let us begin by just generating 434 hertz. So, this is just one waveform whose frequency is 434 hertz. Now, I am going to generate 435 hertz and bring them close together, and hopefully we will see, or actually we will hear the beats happening. So, I have started mine. Let me bring it closer. You should be able to hear the waxing and waning. So, this is an experiment, you can do it for yourself and check the phenomena of beats. In the next module, we will look at what happens when we combine two oscillators in perpendicular directions, and that would be the subject of the next module.